Inverse functions. What are they? What are they? Inverse functions are functions such that y is equal to f of x and x is equal to m of y. Why? Helps to place data that model harmonic motion. Interesting fact, chickens experience rapid eye movement, or REM, sleep, just like dogs and cats. Now, before we talk about inverse functions, we need to talk about functions. Remember, functions have a relationship between the domain and the range, or the input and the output, or the independent variable and the dependent variable. Now, let's take a quick look at some mapping diagrams. Which one do we think is a function? That is correct, the one on the left, because every input has one output. The one on the right, the number 1, has 2 outputs. Now, another way of testing this is to do the vertical line test, which states, during the vertical line test, if the vertical line only intersects the function at most once, then the graph represents a function. One of the keywords here is at most once, so that could mean 0 or 1. So which graphs do we think represent functions? That is correct, the first, second, and fourth ones, because the third one, the vertical line, passes the graph twice. Next, we have the horizontal line test, which states, during the horizontal line test, if the horizontal line only intersects the function at most once, then the graph represents a one-to-one function and has an inverse function. Whoa. Let's talk about one-to-one. The definition states, a function f with domain D in range R is a one-to-one function if either of the following equivalent conditions is met. Condition 1. Whenever a does not equal b in the domain, then f of a does not equal f of b in the range. So if two inputs are not the same value, then their outputs are not the same. Condition 2. Whenever f of a is equal to f of b in the range, then a is equal to b in the domain. So if two outputs are the same value, then their inputs are the same. What does this gibberish even mean? Well, let's look at some diagrams. Which one do we think is a one-to-one function? That is correct, the one on the left, since every input value has one output, and the one on the right is not, because it has two input values that have the same output. Now that we have that, let's go back to the definition of the horizontal line test. During the horizontal line test, if the horizontal line only intersects the function at most once, then the graph represents a one-to-one function and has an inverse function. Let's take a look at some diagrams. Which ones do we think are one-to-one? That is correct, the first, second, and fourth ones, because the third one, the horizontal line, passes the graph twice. Another way to tell if functions are one-to-one is the theorem on increasing or decreasing functions are one-to-one. Part 1 says a function that is increasing throughout its domain and range is one-to-one. Part 2 says a function that is decreasing throughout its domain and range is one-to-one. Let's look at some diagrams. The one on the left is always increasing, and the one on the right is always decreasing. So both of these functions are one-to-one. Now, we are ready to talk inverses. The definition states, let f be a one-to-one function with domain D in range R. A function m with domain R in range D is the inverse function of f, provided the following condition is true for every x in D and every y in R, where we have y is equal to f of x if and only if x is equal to m of y. What does this gibberish even mean? Let's look at some diagrams. Now, on the left, we have an input, x, that travels to the range and has an output, y, or f of x. Next, on the right, we have the same sets, but the range becomes the domain, and the domain becomes the range of the inverse function. So the new input, y, or f of x, travels to the range and has a new output, m of y, or x. Now, let's take a look at the theorem on inverse functions. Let f be a one-to-one function with domain D in range R. If m is a function with domain R in range D, then m is the inverse function of f, and if and only if both of the following conditions are true. Condition 1. M of f of x is equal to x for every x in D. So if the output of the original is put in as the input of the inverse, and the result is x. Condition 2. F of m of y is equal to y for every y in R. So if the output of the inverse is put in as the input of the original, the result is y. Once again, what does all this gibberish mean? Well, let's look at some diagrams. On the left, we have condition 1. So the input, x, travels to the range and has an output, f of x, which travels back through the inverse, and the result is m of f of x, or x. For condition 2, once again, we have the same sets, but the range becomes the domain, and the domain becomes the range of the inverse function. So, the new input of the inverse, y, travels to the range, and has a new output, m of y, or x, which travels back through the original function, and the result is f of m of y, or y. Now, here's a new diagram that might help explain. This time, we're only using notation from the original function. So the domain of the inverse is the range of the original function, and the range of the inverse is the domain of the original function. Lastly, before we do an example with numbers, we need to talk about onto functions. And the definition states, a function f with domain D in range R is an onto function if and only if every element in R maps to every element in D, such that f of a is equal to b. Now, what does this new gibberish even mean? Well, let's look at some diagrams to test this out. Which one do we think is an onto function? That is correct, the one on the left, since every output has an input, and on the right is not, since one output does not travel back. Now, let's read some guidelines for finding the inverse function. The first one is, verify that f is a one-to-one function throughout its domain. The second one is, solve the equation y is equal to f of x for x in terms of y, obtaining an equation of the form x is equal to f inverse of y. The third one is, verify the following two conditions. A, f inverse of f of x is equal to x for every x in the domain of f. B, f of f inverse of x is equal to x for every x in the domain of f inverse. At last, let's take a look at an example with numbers. So we have f of x is equal to 2x minus 1, and f inverse of x is equal to x plus 1 over 2. Each function has an xy table ready to be plotted. What do we notice about the points from the original function and the inverse function? How are they the same? How are they different? That is correct. The x's and y's have flipped location in the xy table of the inverse function, just like all those mapping diagrams. Now, let's graph both of these functions. What do we notice here? That is correct. The line y is equal to x is the line of symmetry, or cuts the graph in half. So if we fold the graph on that line, y is equal to x, the graphs will overlap. Why is it that line? Well, y is equal to x is the OG. It is the first line we talk about, and is the only line where the input is the same as the output. The last bit we're going to talk about is how to verify if two functions are inverses without a graph. Here we substituted the inverse function into the original function and simplified, and the result is x. Really, f of f inverse of x is equal to x, or f of x is equal to x, or y is equal to x. Look at that, just like the dotted line on the graph. Now, we could also substitute the original function into the inverse function. The steps will be different, but the result is the same. And there we have it. So what are inverse functions? And remember, there is always tomorrow.